I've been staring at this data for what feels like a lifetime, but in reality, it's only been a few months since the initial alarm bells went off. My desk is a graveyard of printouts, each one showing a slightly different iteration of the orbital solution for 3I Atlas. The name itself, 3I Atlas, is a clinical designation, the third interstellar object we've confirmed, discovered by the Asteroid Terrestrial Impact Last Alert System, but to me, and to the small, intense team I work with here at the Jet Propulsion Laboratory, it's become something far more personal, a cosmic puzzle that has consumed our every waking thought. The problem, the core of the anomaly that has us working these impossible hours, is a deviation, not a small, expected drift, but a sharp, undeniable change in its trajectory that defies the simple, elegant laws of Newtonian mechanics. When we first identified 3I Atlas, its interstellar nature was immediately apparent. Its orbital eccentricity, a measure of how much its path deviates from a perfect circle, was calculated to be around 6.139. For context, anything over 1.0 is a hyperbolic orbit, meaning the object is moving too fast to be gravitationally bound to our Sun. It's a visitor, a transient guest from another star system, passing through our cosmic neighborhood before heading back out into the void. The initial calculations were clean, a perfect hyperbolic curve dictated solely by the gravitational influence of the Sun and the major planets. We had its ephemeris, its predicted position for every moment in time, and for a while, the observations matched the predictions with unnerving precision. But then, the residuals started to grow. In orbital mechanics, a residual is the difference between where we observe an object to be and where our model predicts it should be. For a purely gravitational orbit, these residuals should hover near zero, a tiny scatter reflecting measurement error. When I first saw the trend, I dismissed it. A calibration error, perhaps. A slight misalignment in the telescope's tracking. I've been doing this long enough to know that the universe is messy, and sometimes the instruments lie. I ran the data through our pipeline again, cross-referencing observations from the Pan-STARRS survey, the Catalina Sky survey, and even the initial Atlas discovery images. The result was the same. The residuals were not random, they were systematically increasing, and in a specific direction. The comet was accelerating, or more accurately, being pushed in a way that gravity alone could not explain. The deviation was subtle at first, a few hundred kilometers off the mark, but as 3I Atlas drew closer to the Sun, the effect became pronounced. We're talking about a change in velocity that, when integrated over the vast distances of space, translates to a significant alteration of its path. It's like watching a billiard ball roll across a table, perfectly predictable, until suddenly a tiny, invisible jet of air nudges it just enough to miss the pocket entirely. That invisible jet of air, in the case of a comet, is almost always sublimation. This is where the science gets complicated, and where 3I Atlas has forced us to rewrite our understanding of interstellar comets. In a typical solar system comet, the heat from the Sun causes volatile ices, primarily water ice, to turn directly into gas, a process called sublimation. This gas streams away from the nucleus, forming the coma and the tail. Crucially, this outgassing acts like a tiny rocket engine, imparting a non-gravitational force on the nucleus. We have sophisticated models, developed over decades, to account for this. They assume that the outgassing is mostly directed away from the Sun, as the Sun-facing side is the warmest. This force is predictable, and we can model it with a high degree of accuracy using parameters like the comet size, rotation rate, and composition. But 3I Atlas didn't behave like a typical comet. The initial light curve was perplexing. It brightened far more rapidly than a water-ice-dominated body should at its distance from the Sun, which was still outside the snow line where water ice typically begins to sublimate en masse. This immediately suggested the presence of supervolatiles, ices that vaporize at much lower temperatures, such as carbon monoxide, CO, or carbon dioxide, CO2. I remember the moment we confirmed the presence of CO in the coma. It was a late night staring at the spectral data from the Keck Observatory. The signature was unmistakable, a clear indication that this interstellar visitor was shedding material far more aggressively than its solar system cousins. The non-gravitational acceleration we calculated was massive, far exceeding what could be explained by a standard water ice model, even accounting for the early onset of CO sublimation. We modeled the force vector, and this is where the sharp change truly became a crisis. The force was not simply anti-solar, it had a significant component perpendicular to the Sun-comet line, suggesting an asymmetry in the outgassing that was highly unusual. It was as if the tiny rocket engine wasn't firing straight back, but slightly to the side, consistently, over a period of weeks. I spent days running simulations, trying to find a physical configuration that could produce this vector. A highly oblique rotation axis? possible, but the required angle was extreme. A localized, powerful jet on the side of the nucleus? More plausible, but the coma, as observed by the Hubble Space Telescope, was remarkably smooth and symmetric. Hubble gave us the sharpest view, resolving the coma down to its innermost regions, and what we saw was a beautiful, almost perfectly spherical glow, with smooth gradients. No obvious, powerful jet was visible, which is what you would expect from a localized force strong enough to produce the observed path change. This contradiction, a massive, asymmetric non-gravitational force, yet a symmetric, featureless coma, is the heart of the 3I Atlas mystery. It forced us to consider two radical possibilities, both of which challenge our fundamental understanding of cometary physics. The first possibility is that the outgassing is not coming from a single, localized jet, but from a vast, distributed network of tiny vents across the entire surface, a phenomenon we've started calling cryovolcanism. Imagine the nucleus of 3I Atlas not as a dusty snowball, but as a porous carbonaceous sponge, saturated with highly volatile ices. As the sun's heat penetrates the surface, it doesn't just create a single plume, it causes countless micro-eruptions across the entire sunlit hemisphere. If the nucleus is rotating, and if the density of these supervolatiles is slightly unevenly distributed, a net force could be generated that is not purely anti-solar. The individual jets would be too small to resolve, blending into the smooth, symmetric coma we observe, but their collective integrated force could account for the sharp change in path. This idea is supported by the hypothesis that 3I Atlas is a primitive carbonaceous object, potentially older than our own solar system. If it formed in the cold, dark reaches of another star's Oort cloud, it would have retained a far higher fraction of these supervolatiles than any comet we've studied that formed in our own system. It's a pristine sample of interstellar matter, and its behavior is a direct reflection of its alien origin. The sharp change in path, in this context, is simply the signature of a different kind of ice, a different kind of cosmic architecture. But there is a second, more dramatic possibility that has gained traction, particularly among some of my more provocative colleagues. This hypothesis suggests that the non-gravitational force is not due to sublimation at all, but to the disruption of the nucleus. We know that comets are fragile. As they approach the sun, the combination of tidal forces and thermal stress can cause them to fragment. We've seen it happen many times, but 3I Atlas's fragmentation, if that's what it is unlike anything we've witnessed. The hypothesis, which I initially resisted but now must consider seriously, is that the comet is not just breaking into a few large pieces, but is shedding a vast, dense swarm of kilometer-sized or smaller objects. The argument is compelling because it addresses the force vector issue. If the comet is shedding a swarm of fragments, and those fragments are then being pushed by solar radiation pressure, the collective momentum transfer could mimic a non-gravitational force. More importantly, if the shedding is asymmetric, say, a massive chunk breaks off the side, the sudden change in the center of mass and the subsequent push from the fragment swarm could easily produce the sharp lateral component of acceleration we observed. The most recent data, which is still being processed and verified, seems to lend credence to this disruption model. We've started to see a faint, sun-facing, anti-tail structure. This is a phenomenon where dust particles, pushed by solar radiation pressure, appear to stream towards the sun from our perspective, due to the geometry of the orbit. But the material in this anti-tail appears to be unusually dense and composed of larger, slower-moving particles than typical cometary dust. My colleague, Dr. Avi Loeb, has gone so far as to suggest that this anti-tail is not dust at all, but the visible signature of the aforementioned swarm of objects, a trail of debris left by a nucleus that is actively disintegrating. I find myself in a difficult position. As an analyst, my job is to find the simplest, most elegant explanation that fits all the data. The sublimation model, enhanced by supervolatiles and cryovolcanism, is the most conservative and scientifically grounded explanation. It requires no new physics, only an adjustment to our understanding of interstellar cometary composition. It explains the rapid brightening and the smooth coma. However, the magnitude and the direction of the sharp path change are so extreme that the fragmentation model, while more radical, provides a more natural fit for the observed force vector. If the nucleus is a loosely bound rubble pile, which many comets are, the stress of its first close pass to the sun in millennia could be enough to trigger a catastrophic yet gradual breakup. The sharp change in path would then be the result of a major mass loss event, a sudden shift in the object's momentum as a large fraction of its mass is jettisoned. The implications of this are profound. If 3I Atlas is fragmenting, it means we are witnessing the death of an interstellar object, a process that has never been observed in such detail. It gives us a unique opportunity to study the interior structure of a body that originated outside our solar system. We could potentially analyze the fragments, which are essentially pieces of a star system that existed billions of years ago, before our own sun was even born. The data from the James Webb Space Telescope, which has the sensitivity to analyze the composition of the fragments, is eagerly awaited. But I must address the elephant in the room, the speculation that inevitably arises when an object behaves in a way that defies our models. The question of whether 3I Atlas could be artificial, a piece of technology rather than a natural phenomenon, is one that has been whispered in the hallways and shouted in the media. I understand the fascination. The first interstellar object, Oumuamua, exhibited non-gravitational acceleration that was even more difficult to explain, leading to the infamous light sail hypothesis. With 3I Atlas, the evidence points overwhelmingly to natural causes, the presence of CO and CO2, the clear spectral signature of ices, the formation of a coma and a tail. These are all classic cometary features. The sharp change in path, while anomalous, can be explained by either enhanced cryovolcanism or fragmentation, both of which are natural processes. The difference between 3I Atlas and a solar system comet is one of degree and composition, not one of kind. It is an extreme comet, an exotic comet, but a comet nonetheless. My job is to find the natural explanation, and I believe we are very close to a consensus. The non-gravitational force is the result of mass loss, whether it's in the form of gas or fragments. The sharpness of the path change simply reflects the intensity of that mass loss as it nears perihelion. My current focus is on refining the rotation model. If we can accurately determine the spin axis and rotation rate of the nucleus, we can better model the distribution of the outgassing vents. We are using a technique called light curve inversion, which involves analyzing the subtle changes in the comet's brightness over time. If the nucleus is irregularly shaped, its rotation will cause periodic dips and peaks in the light curve. If we can map those, we can infer the shape and, crucially, the orientation of the nucleus relative to the Sun. This will allow us to test the cryovolcanism model with much greater rigor. If the model holds, the non-gravitational force vector should align perfectly with the predicted asymmetry of the outgassing. The data we receive is a constant stream, a torrent of numbers and images from telescopes all over the world. We have a dedicated pipeline that processes the raw CCD images, corrects for cosmic rays and instrument artifacts, and then feeds the astrometric data, the precise position measurements, into our orbital fitting software. The fitting process is an iterative one, where we start with a basic gravitational model and then introduce non-gravitational parameters, adjusting them until the residuals are minimized. The sharp change in path is encoded in these parameters, specifically the A1, A2, and A3 coefficients, which represent the non-gravitational acceleration in the radial, transverse, and perpendicular directions, respectively. The A2 coefficient, the transverse component, is the one that truly caught my attention. A large A2 means the comet is being pushed either forward or backward along its orbital path. A positive A2 means it's being accelerated, which is what we observed. This is the component that causes the sharp change in the path, because it alters the object's orbital period and, in a hyperbolic orbit, its asymptotic velocity. It's the signature of a force that is actively changing the comet's destiny, ensuring it leaves our solar system on a slightly different and faster trajectory than it entered. The sheer scale of the data is daunting. We are talking about thousands of observations, each one a tiny point in a vast multidimensional space. The challenge is not just to fit the data, but to ensure that the fit is physically meaningful. We can always find a mathematical solution that minimizes the residuals, but if that solution requires a non-gravitational force that is physically impossible, say, a force that is 10 times stronger than what sublimation can produce, then the model is flawed. This is why the composition is so critical. If 3I Atlas is indeed rich in CO, which is far more volatile than water, the mass loss rate for a given amount of solar heating is exponentially higher. A small patch of exposed CO ice could produce the same non-gravitational thrust as a much larger area of water ice. The sharp change in path, therefore, might be a consequence of a sudden exposure of a large reservoir of CO ice, perhaps due to a small impact or a thermal fracture. I've been working with the team to develop a new thermal model that incorporates the multi-layered composition of an interstellar comet. We hypothesize a structure, a refractory, carbonaceous crust, beneath which lies a layer of water ice, and deeper still, a core rich in supervolatiles like CO and N2. As the comet approaches the Sun, the crust fractures, exposing the CO layer, leading to a massive, sudden burst of outgassing, the sharp change. As the CO is depleted, the outgassing rate drops, and the non-gravitational force diminishes, only to potentially surge again when the water ice layer is exposed. This cyclical behavior, a series of sharp changes followed by periods of relative calm, is what we are now looking for in the historical data. The most recent data point, the one that arrived just this morning, shows a slight decrease in the non-gravitational acceleration. This is a crucial piece of evidence. If the force were due to a continuous, stable process, like a steady jet, we would expect it to continue or even increase as the comet moves closer to the Sun. The decrease suggests a transient event, a burst of activity that has now subsided. This supports the idea of a sudden exposure and subsequent depletion of a volatile reservoir, or perhaps the end of a major fragmentation event. The sheer magnitude of the path change has also forced us to re-evaluate the object's mass. The non-gravitational force is inversely proportional to the mass of the nucleus. A smaller nucleus requires a smaller force to produce the same acceleration. If 3I Atlas is smaller than our initial estimates, the non-gravitational force we calculated might not be as extreme as it first appeared. The Hubble observations provided a size estimate of the nucleus, suggesting it was relatively small, perhaps a few hundred meters across. This small size, combined with the high volatility of its ices, makes the sharp path change more understandable within the framework of natural cometary physics. It's a tiny, highly energetic object, a cosmic firecracker. The entire episode with 3I Atlas has been a masterclass in the limitations of our solar system-centric models. We have spent decades studying comets that formed in the Kuiper belt and the Oort cloud of our own Sun. We understand their composition, their dynamics, and their response to solar heating. But an object from another star system, formed under different conditions, with a different chemical inventory, is a completely different beast. The sharp change in path is the universe's way of telling us that our models are incomplete, that we need to expand our understanding to encompass the full diversity of cometary objects in the galaxy. I've been collaborating with teams across the globe, from the European Space Agency to the observatories in Chile and Hawaii. This is a global effort, a race against time, because 3I Atlas is moving fast. It is already heading outbound, away from the Sun, and as it recedes, its activity will diminish, and the opportunity to study this sharp change in its path will be lost. We are trying to squeeze every last bit of information out of the data before it becomes a faint smudge in the deep sky once more. The most recent analysis I completed involved a detailed comparison of 3I Atlas's non-gravitational parameters with those of 2I Borisov, the second interstellar object we discovered. Borisov also exhibited non-gravitational acceleration, but it was much milder and more consistent with a standard water-ice sublimation model. The difference between the two is striking. Borisov was a relatively normal comet, just from another star. 3I Atlas is an outlier, an extreme case that suggests a much more violent and volatile history. The sharp change in its path is the quantitative measure of that difference. I've been running a simulation that attempts to reverse engineer the event that caused the sharp change. I start with the current trajectory and run the clock backward, introducing a hypothetical force vector that matches the observed deviation. The simulation suggests that the event was not instantaneous, but a prolonged period of intense activity lasting several weeks, centered around its closest approach to the Sun. The total impulse, the change in momentum, was enormous. It's the equivalent of a small asteroid impact, but generated purely by the internal dynamics of the comet itself. The question that keeps me up at night is whether this sharp change in path is a one-time event or a precursor to total disintegration. If the fragmentation hypothesis is correct, the nucleus may be on the verge of a complete breakup. We've seen comets disintegrate before, but never one of interstellar origin. If 3I Atlas breaks up, the resulting cloud of fragments would be a scientific goldmine, but it would also pose a minor, though non-zero risk to spacecraft and satellites, as the debris would be moving at interstellar velocities. We are constantly updating the risk assessment, but for now, the probability of impact remains negligible. The work is meticulous, painstaking, and often frustrating. I spend hours in front of a screen, adjusting parameters in a complex differential equation solver, trying to find the sweet spot where the physics aligns with the observation. I am constantly battling the noise in the data, the subtle biases introduced by the instruments, and the inherent uncertainty of working with an object that is hundreds of millions of kilometers away. But every time I see the residuals drop, every time the model snaps into place, I feel a surge of pure scientific satisfaction. The sharp change in 3I Atlas's path is not just a curiosity, it is a data point that will fundamentally change how we approach the study of interstellar objects. It tells us that these visitors are not just passive travelers, they are dynamic, volatile bodies that can undergo rapid, dramatic changes as they interact with our Sun. It suggests that the interstellar medium is a rich repository of chemically diverse objects, far more varied than the comets that formed in our own solar nebula. I remember the initial press conference, the cautious language we used, the emphasis on non-gravitational acceleration. The public wants a simple answer, a headline. But the reality is a complex interplay of thermal physics, orbital mechanics, and exotic chemistry. The sharp change is the observable manifestation of a process that began billions of years ago in another star system, a process that is now culminating in a spectacular display of cometary activity right here in our solar system. My next step is to integrate the latest spectral data, which shows a clear depletion of CO relative to the dust production. This is the smoking gun for the transient event hypothesis. The CO burst that caused the sharp path change has likely subsided, and the comet is now transitioning to a water-ice-dominated outgassing phase, or perhaps a dust-dominated fragmentation phase. The force vector should now be shifting back towards the anti-solar direction, and the magnitude should be decreasing. If the next set of astrometric data confirms this trend, we will have a complete picture of the event. The legacy of 3I Atlas will be defined by this sharp change. It is the moment when a seemingly predictable hyperbolic trajectory became a complex, dynamic dance. It is the moment when we realize that interstellar comets are not just passing through. They are actively responding to our Sun, revealing their secrets in the process. And I, as one of the analysts who first spotted the deviation, feel a profound connection to this tiny, volatile visitor from the deep past. It is a privilege to be a witness to this cosmic event, and my work continues, driven by the need to understand every kilometer of its extraordinary, sharply changed path. The sheer volume of the data is what truly distinguishes this work. We are not just looking at a handful of observations. We are integrating data from the entire network of NASA's Deep Space Network, which provides the highest precision astrometry available. The DSN antennas, primarily designed for tracking spacecraft, are occasionally repurposed for high-precision tracking of near-Earth objects and, in this case, interstellar visitors. The precision of the DSN data is what allowed us to detect the subtle, initial deviation before it became a sharp change. Without that level of accuracy, the non-gravitational acceleration would have been masked by the noise of less precise instruments. I've been working closely with the team that manages the DSN scheduling. It's a constant negotiation, trading time on the massive 70-meter dishes for a few precious hours of tracking 3I Atlas. Each tracking session provides a series of range and range rate measurements, which are far more sensitive to changes in velocity than simple angular position measurements. The range rate data, in particular, is what truly illuminated the sharp change. It showed a sudden, sustained acceleration that was impossible to attribute to gravitational forces. It was a clear, unambiguous signal of a force acting on the comet's center of mass. The mathematical framework we use is the standard cometary model developed by Marsden, Sekanina, and Yeomans, but we've had to push its limits. The model uses a set of empirical parameters to describe the non-gravitational force, assuming it is proportional to the solar flux and directed generally away from the Sun. For 3I Atlas, we had to introduce a time-dependent component to these parameters, essentially allowing the non-gravitational force to turn on and turn off rapidly. This is the only way we could fit the data that showed the sharp increase in acceleration followed by the recent slight decrease. I remember the moment I first plotted the time-dependent A2 coefficient. It looked like a step function, a sudden jump from a near-zero value to a significant positive value, and then a gradual decay. This plot, more than any other, is the visual representation of the sharp change. It's not a smooth curve, it's a discontinuity, a break in the expected behavior. It suggests a catastrophic event on the nucleus, a sudden exposure of a massive volatile reservoir. The fragmentation hypothesis, which I mentioned earlier, has become increasingly difficult to dismiss. If the comet is indeed shedding a swarm of objects, the sharp change in path could be a result of the collective momentum of the ejected material. Imagine a massive but slow explosion. The fragments, once ejected, are then subject to their own orbital mechanics, but the reaction force on the main nucleus is what we measure as the non-gravitational acceleration. The problem is that the fragments themselves are too small and too faint to be individually tracked with current instruments, at least not in the inner coma. We are looking for the collective signature, the subtle broadening of the coma that suggests a population of slow-moving debris. The latest images from the Hubble Space Telescope, which were taken just a few weeks ago, are our best hope for resolving this. Hubble's resolution is unparalleled, and the team has been using a technique called stacking to enhance the signal-to-noise ratio. They are looking for subtle asymmetries in the dust trails, faint streaks that would indicate the direction of the fragmentation. If we can confirm the direction of the debris ejection, we can directly compare it to the direction of the non-gravitational force vector we calculated. A perfect alignment would be the definitive proof of the fragmentation model. I've been running a parallel analysis, focusing on the energy budget of the comet. The amount of energy required to produce the observed non-gravitational acceleration is immense. If the force is purely due to sublimation, we can calculate the mass loss rate required. This mass loss rate, when compared to the observed brightness of the coma, gives us a measure of the dust-to-gas ratio. For 3I Atlas, the numbers are highly unusual. The required gas production rate is so high that it suggests the comet is almost pure volatile ice, with very little refractory material. This contradicts the primitive carbonaceous object hypothesis, which suggests a high dust content. This is the central tension in our analysis. The dynamics suggest a massive gas production, while the composition suggests a dusty, carbon-rich body. This tension is what makes the sharp change so scientifically valuable. It forces us to reconcile two seemingly contradictory pieces of evidence. One possible reconciliation is that the carbonaceous material is not dust, but a highly porous, low-density matrix that is easily blown away by the sublimating gas. In this scenario, the comet is shedding both gas and dust at an enormous rate, but the dust is so light and fluffy that it doesn't significantly contribute to the non-gravitational force. The sharp change in path is then the result of a massive, simultaneous ejection of both gas and low-density dust. I've been working on a visualization of the comet's trajectory, a three-dimensional model that allows us to see the sharp change in context. When you look at the entire hyperbolic path, the deviation is a tiny, almost imperceptible kink. But when you zoom in on the perihelion passage, the kink becomes a sharp, dramatic turn. It's a testament to the power of our analytical tools that we can detect such a small change over such vast distances. The visualization is a powerful tool for communicating the significance of the discovery, but for me, the true significance lies in the numbers, in the A2 coefficient that spiked so dramatically. The work has also involved a deep dive into the history of cometary dynamics. I've been reading the original papers on the non-gravitational forces in comets, the foundational work that established the current models. It's a humbling experience to realize that the sharp change in 3I Atlas's path is forcing us to revisit and potentially revise these decades-old models. The original models were based on the assumption of a relatively uniform, water-ice-dominated composition. 3I Atlas, with its interstellar origin and super-volatile content, is the ultimate test case for these assumptions. I've also been collaborating with the team that studies the formation of interstellar objects. They are running simulations of star formation in dense molecular clouds, trying to understand the conditions that would lead to the formation of a comet with such a high CO content. The sharp change in path is, in a way, a window into the chemistry of another star system. The magnitude of the non-gravitational force is a direct measure of the volatility of the material, which in turn is a measure of the temperature and pressure in the protoplanetary disk where 3I Atlas was born. The latest analysis I performed involved a statistical study of the residuals. I used a technique called a Monte Carlo simulation, where I ran thousands of hypothetical orbits, each with slightly different initial conditions and non-gravitational parameters, to see which ones best fit the observed data. The results were clear. The only way to fit the data is to include a sharp, transient increase in the non-gravitational force. Any model that assumes a smooth, continuous outgassing fails to reproduce the observed trajectory. The sharp change is not an artifact of the data, it is a real, physical event. I've been preparing a technical report on the findings, a document that will be submitted to a peer-reviewed journal. The report is a dense mathematical exposition of the orbital fitting process, the calculation of the non-gravitational parameters, and the physical interpretation of the sharp change. It's a document that will be scrutinized by the entire cometary science community, and I am determined to ensure that every claim is supported by verified data and rigorous analysis. The title of the paper, which I've been debating with my colleagues, will likely focus on the extreme non-gravitational acceleration and transient activity of interstellar comet 3I Atlas. The final piece of the puzzle, the one that remains elusive, is the rotation state. If we can lock down the rotation period and axis, we can definitively choose between the cryovolcanism and fragmentation models. A slow, stable rotation would favor the fragmentation model, as the thermal stress would be more localized and intense. A rapid tumbling rotation would favor the cryovolcanism model, as the outgassing would be more evenly distributed, leading to the observed symmetric coma. The Hubble team is working on this, and their results will be the final piece of evidence we need to fully understand the sharp change in 3I Atlas's path. I look at the plot of the residuals one last time before I log off for the night. The sharp spike, the undeniable evidence of a force beyond gravity, is a reminder of the vastness and complexity of the universe. We are not just tracking a rock in space, we are tracking a piece of another star system, a messenger from the deep past, and its erratic, sharply changed path is a story waiting to be fully told. The sheer complexity of the orbital mechanics, the thermal modeling, and the compositional analysis required to explain this one sharp change in path is a reflection of the profound scientific challenge that 3I Atlas represents. I've been thinking about the sheer energy involved in this event. To produce a non-gravitational acceleration of this magnitude, the comet must have shed an incredible amount of mass. If we assume the mass loss is primarily water ice, the required mass loss rate is unsustainable for a nucleus of its estimated size. This is the strongest argument for the supervolatile hypothesis. Carbon monoxide, for instance, has a much lower latent heat of sublimation than water ice. This means that for the same amount of solar energy absorbed, CO ice can produce a much larger volume of gas, and thus a much larger non-gravitational force. The sharp change in path is, therefore, a direct consequence of the comet's exotic interstellar chemistry. It's a chemical signature written in the language of orbital dynamics. The process of orbital fitting itself is a delicate balance of art and science. We use a weighted least squares method, where the weight of each observation is determined by its precision. The DSN data, being the most precise, carries the highest weight, and it is the DSN data that most clearly shows the sharp change. When we first introduced the non-gravitational parameters into the fit, the reduction in the overall root mean square residual was dramatic. It was the mathematical confirmation that the deviation was real, not an artifact. The sharp change was not a gradual drift, it was a sudden, powerful impulse. I've also been exploring the possibility of a rotational burst. If the comet has a highly elongated shape and a sudden powerful jet erupts from one of its ends, it could not only accelerate the comet but also induce a rapid change in its rotation rate and axis. This is a complex coupled problem. The non-gravitational force affects the orbit, and the change in rotation affects the outgassing pattern, which in turn affects the non-gravitational force. It's a feedback loop that could explain the transient nature of the sharp change. I've been running simulations of this rotational burst model, and the results are promising. A single powerful jet, lasting for a few days, could account for both the sharp path change and the subsequent decay in the non-gravitational acceleration. The scientific community is divided on the interpretation, which is a healthy sign of a major discovery. Some favor the fragmentation model, pointing to the unusual anti-tail and the high dust-to-gas ratio. Others, including myself, lean towards the cryovolcanism model, arguing that the symmetric coma is a strong counter-argument to a major asymmetric fragmentation event. The sharp change in path is the common ground, the undeniable fact that both sides must explain. It is the anchor point for all our theories. I've been working on a detailed timeline of the event, correlating the sharp change in the orbital parameters with the photometric data, the measurements of the comet's brightness. The correlation is striking. The sharpest increase in the non-gravitational acceleration perfectly coincides with the most rapid increase in the comet's brightness. This is the most compelling evidence that the sharp change is directly linked to a massive increase in the comet's activity, a sudden, powerful release of volatile material. The path change and the brightening are two sides of the same coin, the dynamic and photometric signatures of a single powerful event. The long-term implications of this discovery are what truly excite me. If interstellar comets are routinely this volatile, if they are capable of such sharp, dramatic changes in their paths, it has profound implications for the dynamics of the interstellar medium. It suggests that the population of interstellar objects passing through our solar system is not a collection of inert, predictable bodies, but a dynamic, evolving population. It also raises the possibility that some of the unexplained deviations in the orbits of other comets, which we previously attributed to measurement error, might actually be the subtle signatures of similar, smaller-scale non-gravitational events. I've been reviewing the data from the initial discovery of 3I Atlas, the images taken by the Atlas survey telescopes. Even in those early images, when the comet was still far from the Sun, there were subtle hints of activity, a faint, extended coma that was unusual for its distance. This suggests that the supervolatiles were already sublimating even in the cold, outer reaches of the solar system. The sharp change in path was not a sudden, unexpected event, but the culmination of a long, slow process of thermal evolution. The comet was a ticking time bomb of volatile ice, and its close approach to the Sun was the trigger. It is a narrative that weaves together data from multiple telescopes, complex mathematical models, and the collective knowledge of the entire cometary science community. The sharp change is the plot twist, the moment of crisis that forces us to question everything we thought we knew. I've been running a final set of simulations, a what-if scenario where I assume the sharp change was caused by an entirely different mechanism, such as a close encounter with a small, unobserved asteroid. The results are clear. A gravitational perturbation would produce a completely different signature in the residuals. The non-gravitational force is the only mechanism that can reproduce the observed acceleration vector. The sharp change is a testament to the power of internal cometary dynamics, not external gravitational influence. The work is far from over. Even as 3I Atlas recedes from the Sun, the data continues to pour in.